Hello, I'm Tony Thornton, Director of Technical Information here at Micromeritics. I want to thank all of you for attending our demonstration on how to use the AutoPore Mercury Intrusion Porosimeter. This demo will include video of our senior AutoPore analyst, Chris, performing various important operations on the AutoPore, as well as a presentation by me on some important features of AutoPore software and reporting. Between the two of us, we have over 55 years of experience and have used a wide range of mercury porosimeters. Over the years, we've learned these techniques to maximize quality results from an AutoPore, which we will share with you today during this demo. So let's begin. First, Chris will demonstrate loading a sample into an empty penetrometer and then sealing the penetrometer for analysis using the AutoPore. He will determine and record the sample mass as well as the penetrometer mass, both of which are needed for calculations of specific intrusion volume and material densities. Initially, Chris is going to determine the mass of the sample test portion. Today, he is analyzing an alumina catalyst support. Now, Chris has analyzed materials like this before and wants about 1 gram of sample. We need to analyze enough sample so that 25% to 90% of the mercury available for intrusion is used during the analysis. And so the penetrometer being used helps to determine the mass of sample needed, as does the porosity of the sample. He starts with tearing the balance with a weighing pan, adding the sample, and recording the mass in his laboratory notebook. Next, Chris is going to prepare to add sample to the penetrometer by placing a small piece of pipe cleaner into the top of the stem. When analyzing extrudates, such as this catalyst support, we use one of the powder penetrometers. For these, the stem extends up into the bowl. This helps to prevent sample from entering the stem during handling and analysis. The pipe cleaner makes it easier for Chris to add the sample to the bowl without sample entering the penetrometer stem. He uses the same technique when analyzing powdered samples. He tamps the penetrometer lightly to settle the sample and discards the piece of pipe cleaner. He's going to place the weighing pan back onto the balance to make sure he transferred all the sample to the penetrometer. Now it is time to seal the penetrometer. Chris starts by placing a line of the APazon H grease on his finger. He's going to apply this grease in a thin line along the outer edge of the top surface of the penetrometer by rotating and lifting the penetrometer along the line of grease on his finger. He moves his finger around the outer edge of the penetrometer to remove any excess grease. Notice the nice even line of grease around the top of the penetrometer. We do not want any grease on the inside of the bowl, as this can get onto the sample, blocking some pores. He places the cap onto the top of the pen and rotates it to spread the grease into a uniform layer around the outer edge of the penetrometer sealing surface. He wants to make sure he has the cap centered on top of the penetrometer and evenly seated on the layer of grease. It is important that the grease is uniformly distributed under the cap and that there are no air bubbles present in the film of grease that could be points where the seal could leak. Chris holds the penetrometer up so that he can look through the penetrometer sealing surface to determine visually that he has a uniform seal. He adds the sealing nut and tightens it snugly. The mass of penetrometer is needed to determine the sample densities, and since the amount of grease used each time may vary, a new penetrometer mass is needed for each analysis. Chris will tear the penetrometer weighing support on the balance and record the mass of penetrometer plus sample. He will subtract the sample mass to obtain the penetrometer mass. The sample is now ready for analysis using the AutoPore. Next, we will begin a low-pressure analysis for the sample just prepared. We start by creating a sample information file, and there are several ways to accomplish this. For the analysis, we will use the File menu to open a new file entitled Catalyst Support. We will use our default method to set most of the analysis parameters that we routinely use for sample analyses. We will identify the sample, the operator, and the submitter of this sample to be analyzed. We then select the penetrometer that Chris is using for this analysis and update its mass along with the sample mass. The assembly mass will be added after the low pressure analysis is complete. We can now save the file as our default method includes all the standard analysis and reporting parameters. Chris is going to insert the penetrometer in the sample just prepared to the low pressure port of the instrument. Initially, Chris removes the low pressure capacitance detector assembly along with a transparent retainer from the low pressure port to be used for this analysis. We keep the filler rods in the ports whenever not being used. This will keep the ports cleaner while idle and are needed during analysis in case we're not using all the low pressure ports. All ports must be sealed for the analysis to be performed. Chris takes a sealed penetrometer, adds a spacer to make certain the penetrometer properly contacts the capacitance detector assembly, and carefully inserts the penetrometer in the port. He adds a transparent retainer and tightens the port around the penetrometer stem. He adds the detector assembly, and the sample is ready for analysis. We go back over to the computer to start the analysis using the unit menu, selecting low pressure analysis. We select the port we want to use and load in the sample information file that we just prepared. Since this is the only sample to be analyzed, we will click on Start to begin the analysis. Now we will remove the sample from the low pressure port and determine the assembly mass. This mass represents the mass of the test portion of the penetrometer and of the mercury that was loaded into the penetrometer at the beginning of the low pressure analysis. This is generally before the mercury intrudes into the pores of the sample material. The temperature of the mercury can be used to determine the mercury density, and with the mass of mercury surrounding the sample, the mercury volume can be determined. Knowing the calibrated empty penetrometer volume and the mercury volume surrounding the sample, the volume of mercury displaced by the sample prior to intrusion is the bulk volume of the sample. Along with the sample mass, this allows calculation of the bulk density of the sample. Chris removes the capacitance detector assembly slowly in case mercury is leaked out of the penetrometer and into the detector assembly. The plastic trays below the low pressure ports are there to catch mercury in case a leak has occurred. He then loosens the low pressure port and removes the transparent retainer. Now Chris carefully slides the penetrometer from the low pressure port, being careful not to tip the penetrometer so that mercury doesn't pour from the end of the open stem. Since Chris is not starting another sample in low pressure port right away, he will seal the port with a filler rod with a transparent retainer and a detector assembly in place. The next step is to determine the assembly mass for the penetrometer just removed from low pressure. Since the penetrometer must be in the stem upward orientation, Chris will tare the balance and then set the penetrometer on its cap to determine the mass which he records. This mass will be entered when we begin the high pressure analysis. And that is the next step, loading the sample into the high pressure port and continuing the analysis. It is important to complete this process correctly and completely to make certain that the initial high pressure analysis results match the final low pressure analysis results. The software will start the high pressure analysis at the same pressure as that last low pressure point, but we need to make sure that the pressure transducers match up near ambient pressure. The high pressure system may have just completed an analysis, possibly resulting in some pressure offset at the lower end of the operational range due to hysteresis in the transducer. We can make use of the reading of the low pressure system when idle to adjust any offset in the high pressure transducer. We will do this when we initiate the high pressure analysis. It is important as well that we do not cause any intrusion to take place while tightening the high pressure system. Any intrusion that occurs while tightening will not be recorded by the software, and if it does not fully extrude once tightening is complete, will leave a flat spot in the cumulative intrusion at the crossover point between the low and high pressure portions of the analysis. The instrument software will match the capacitance readings from which intrusion volume is calculated, but cannot account for any intrusion that occurs while data are not being collected. The high pressure port closures are lowered at this point, but not sealed. Chris will raise the closures until the latch engages for each. He will insert the penetrometer into the high pressure port, loading it up into the closure first, releasing the latch to lower the closure slightly, and then seat the penetrometer onto the banana plug in the bottom of the chamber that connects to the high pressure capacitance. Once seated, he will slowly lower the closure until it contacts the top of the high pressure chamber. Since we're only analyzing one sample, he will lower the closure for the other high pressure chamber as well. As with the low pressure system, all high pressure ports must be sealed for the analysis to proceed. Chris slowly tightens the two closures, being careful not to generate pressure that could lead to unrecorded intrusion. Note that the vent valves at the top of the two closures are open while tightening the closures. As Chris closes the left port, some high-pressure fluid can be seen entering the vent valve reservoir. We do not see any yet on the right side. That is because the penetrometer occupies some space in the left chamber, but the right one is empty. Chris will add some high-pressure fluid to the right vent reservoir. To pull that fluid into the right chamber and to help expel air from both chambers, Chris loosens the chambers, then retightens them. Notice that quite a bit of air is coming up into the right vent valve reservoir. After another cycle of loosening and tightening, more high-pressure fluid is needed to fill the right chamber. Chris will repeat loosening and tightening the chambers until very little additional air comes from those chambers. Now we move back to the computer. High pressure analysis is selected from the unit menu. We select the same sample information file and assign it to the high pressure port 1. We update the assembly mass. As mentioned earlier, we will use the low pressure transducer reading to adjust any offset in the high pressure system. To ensure that the low pressure transducer is reading the ambient pressure, loosen one of the low pressure ports. Make sure that the Determine Transducer Offset box is checked and enter the stable value for atmospheric pressure. Now click on Start to resume the analysis of our alumina catalyst support sample. At an appropriate time, the software will instruct you to close the vent valves. Do so and click on OK to continue. Now about that volume calibration for the penetrometer. To calibrate the penetrometer volume, we need to seal the penetrometer, determine its sealed mass, fill it with mercury, then determine the mass after filling. The mass difference will represent the mercury required to fill the penetrometer while empty. Using the density of mercury, the volume of the penetrometer can be determined. The AutoPore 5 includes a temperature sensor near the low pressure system that can be used to determine the density of mercury from a stored table of density versus temperature. The software includes a wizard under the unit menu to help with penetrometer calibration. We recommend that you repeat the determination 3 times and use the average value. You can prepare a penetrometer file that can include the calibrated volume. By selecting the penetrometer when preparing the sample information file for analysis, the volume is loaded automatically. The penetrometer mass will need to be updated as it changes each time the penetrometer is sealed with a different amount of grease. Let's prepare that penetrometer property file for a new penetrometer. It is a 5 cubic centimeter powder penetrometer with a 1.131 cubic centimeter stem volume. This is a type 10 penetrometer. Let's open a new penetrometer property file from the File menu. This is penetrometer 10-0723, and that will be the name of our new file. We will click the drop-down list and select the default parameters for a type 10 penetrometer. Now, when we received this penetrometer, it came with specific penetrometer constant used to convert capacitance change into intrusion volume. What is shown here is a default value, but for this penetrometer, we need to enter 22.285 as the constant. We do not yet know the penetrometer volume and mass, so we will leave that as is, along with the stem volume and maximum head pressure values that are shown currently. Let's enter an identifying name for the penetrometer and save the file. Now let's move back over to the calibration wizard. Click on the drop-down list for port 1 and select our new file. Now we need to seal the penetrometer and determine its empty mass. As with preparing a sample for analysis, we need to seal the penetrometer, only this time doing so without adding sample. Chris starts with a line of apiazon H grease on his finger, then applies it to the penetrometer by rotating and lifting the top of the penetrometer along the line of grease on his finger, effectively removing most of the grease and transferring it to the sealing surface of the penetrometer. He removes any excess grease from the outer edge of the penetrometer and from his finger, and then applies the cap, being careful to align it to the top of the sealing surface. He verifies that the cap is properly aligned on top of the penetrometer and checks for a uniform seal by looking through the penetrometer at the sealing surface. Now he adds the sealing nut and tightens it snugly. We need to know the mass of the empty penetrometer, and so Chris tears the balance and records the penetrometer mass. Since there is no worry for any sample entering the penetrometer stem, it can be turned up and placed on the cap. And we record the mass to use when calibrating the penetrometer. We move back to the computer and enter this mass. We need to install the sealed penetrometer into the low pressure port just as we did earlier when we analyzed the sample, remembering to include the spacer to properly align the penetrometer and the transparent retainer. Once the port is sealed and the detector assembly is in place, we can move back to the computer. We click Fill on the calibration wizard. The penetrometer will be evacuated and filled with mercury. Once filled, we remove the penetrometer to determine the assembly mass. The balance is tared and the penetrometer is placed on the balance. The mass is recorded. We return to the software and enter the assembly mass. The software calculates the penetrometer volume. We then repeat this twice, emptying and cleaning the penetrometer each time. The software calculates the average penetrometer volume and stores it in the penetrometer properties file for future use. Next, we will look at some results for a previously analyzed sample, in this case, a porous powdered material. Now we will show how to adjust the range of the collected data to use when calculating the intrusion and density results for a porous powder sample. So we open the sample information file, and we see it here, porous powder. And we notice that we see two areas of intrusion. Now we know this is a powdered sample, and based upon the size of the powder particles, we actually know that this area in here is filling the interstitial space between the particles that make up the powder. So I move my cursor to the blue line, hold down the left mouse button, and I can move this over, and if you notice the upper left-hand corner, the calculated distribution is changing. I'm going to move this over until we reach that local minima in the log differential curve right here. That marks the end of the interstitial filling, and what we are left with then is the intrusion into the porosity of this sample only. So we edit the intrusion results, but unless we want the bulk density to represent the entire powder bed, if we want particle density instead, we need to adjust the point at which the bulk density is being calculated. So I can click on the box and I can either drag the blue line to the same point, or I can simply read the pressure here, 22.5252 psi, and have it recalculate the bulk density at that point. Now the calculation of bulk density is matching the intrusion only of the pores in the sample and not including the impact of the interstitial space. Now, since this is a porous powder and we may want to understand material properties of our porous material, our pore structure values, we also need to make an adjustment to the threshold pressure used to calculate permeability and tortuosity values for this sample. We're going to move over to the pore structure page, and we see here that the threshold pressure from which the pore structure summary is being calculated is marking the inflection for the interstitial filling. We want it to mark the inflection for the actual porosity. So we're going to grab this and drag it over again to about 22.5 psi. And notice now the threshold pressure is being indicated at the inflection for the actual porosity of the sample, and these values here are being recalculated appropriately based upon the fact that we've removed the interstitial portion of the analysis. Now, if we want to, we can save this file, and we can generate a report. And our report that we've generated now has been adjusted. We can see here that the bulk density is at 22.5 psi. And if we go look at our cumulative curve, we'll see it's only showing intrusion for the into the porosity of the sample. And with our pore structure graphs, we can see that our threshold pressure, again, is marked for the porosity of the sample and not the interstitial filling. Okay, some materials compress under the influence of high pressures used in mercury intrusion analysis, and that there are no pores being filled at those pressures. The reduction in sample size can appear as intrusion into small pores. Mercury must replace the volume that the compressed sample no longer occupies. This mercury appears to be intruding into very small pores since it's taking place at very high pressures, leading to erroneous results. If we know that only compression is occurring, we can use the software to correct for it. So I'm going to use a sample that we know to be compressible to demonstrate compressibility correction. So I go and open the sample information file for my compressible sample. Now, we happen to know that this sample is a polymeric material and likely does not have porosity at these very high pressures. You'll see here that if these were in fact pores, we would be calculating a total pore area of over 6 meters squared per gram. We actually have a BET analysis of this that tells us that it has much lower surface area. So we suspect that this is compressibility up here. Now, we could simply just edit these data out, but there is some compressibility taking place even in the part of the distribution that is pore filling. So rather than just simply truncating the data, let's remove the effects of compressibility. And we can do that by moving to material compressibility portion. Now we see here that it's trying to calculate compressibility values over the entire range of the analysis, and we know that that's not appropriate. So we're just going to move this blue bar over to about here. And now we can see a region up here that seems to be a reasonable fit for a compressibility correction, for calculating compressibility factors. So now I'm going to move this blue bar over, and we can see here now that our fit using these first and second order parameters has essentially no RMS error left over in these data. So we've calculated compressibility values based upon this intrusion that takes place up here. We can see that the extrusion follows it back, and so essentially there's no hysteresis here. That helps to support the fact that we don't believe what's going on up here is the filling of any pores. Let's go back over to the intrusion data now. We'll go to the intrusion data options, and we will tell it to adjust the intrusion for compressibility and to use the coefficients from the compressibility report. And as we see here now, it's nice and flat, and it's showing us a calculated pore area from our pore volume distribution of only 1 square meter per gram. So this helps to confirm what we had suspected, is that this sample was compressible, and we can easily correct its compressibility using this built-in function of the software. So we can save these results and close the file, and we're done. Next, we will look at applying analysis of an empty penetrometer to correct for some of the blank effects in the analysis results. These are caused by heating of the mercury as work is being applied, compression of the sample holder, expansion of the high-pressure chamber, compression of the high-pressure fluid, and so on. So we are going to use the analysis of a controlled pore glass with pores of 3,000 angstroms or 300 nanometers to have a look at this correction for blank effects. Now, if I come in here and turn on report negative intrusion so that I can see some of the maybe flaws that might be going on, we see that this curve turns downward. And that is the effect of heating of the system. The penetrometer contains mercury. Mercury expands as temperature changes. We used to use mercury in thermometers. And as we apply work to a system, in this case we're applying pressure to the mercury, forcing it to move into pores, we can generate a small amount of heat. And we're seeing the impact of that heating of the mercury here. Now we can turn off to report negative intrusion, and it forces the data to be perfectly flat. But we also can go and apply a correction from a blank analysis where we analyze a sample holder empty. If we go over here to our analysis parameters, we can see that a type 10 penetrometer was used in this analysis. And I happen to have a blank analysis from a type 10 penetrometer, a similar one. It's not exactly the same penetrometer, but it is one that behaves closely enough. And when I apply this, now I see a slight upward turn in my results, which means that I am probably seeing a little compressibility effect here, but I've essentially removed the effects of the negative going data. It's not turning downward anymore. Rather than by truncating it, I can actually turn on, or I can apply this blank correction to correct for those blank errors that occurred during an analysis. And last but by no means least, let's discuss the values typically shown in an intrusion summary. So let's go open an analysis of a sample. In this case, this happens to be our reference material. It's also a catalyst support. And we see here the typical intrusion summary. Many people have asked, what do all of these mean? Okay, so total intrusion volume. That is the total volume, or the cumulative volume, at the highest point in the analysis. So we can consider that to be the total volume of all the pores once they're filled. Now, from a pore volume distribution, we can calculate a pore area distribution. If we go over here and have a look at the tabular data, we can look at the incremental volume amounts and the diameters of the pores being filled. And from the volume versus area relationship of a cylinder, we can calculate the area of the pores, the wall area inside the pores being filled from the incremental pore volume and the pore diameter. The equation is area equals 4 times volume divided by diameter. Again, from the geometry of a cylinder. And then we can add those up. We can accumulate the pore area for each point to get a total pore area shown here. So if we go back over to our intrusion summary, we see that total pore area. Now going back to our cumulative intrusion curve, this is our cumulative pore volume here. Let me get rid of this overlay right quick. There we go. So I see here my cumulative intrusion volume at my highest pressure, my total pore volume, is about 0.52. If I take 1/2 that value, which is at about 0.26, and I find the corresponding diameter that matches that, that's my median pore diameter from the volume distribution. And for this sample, that occurs, that happens to be 0.0912 micrometers, or 9.12 nanometers. And as we see that occurs at a pressure corresponding to 23,643 or so pounds per square inch, and the volume at that point is in fact 1/2 of our total intrusion volume. Now, if we take 1/2 of our total pore area, our pore area we calculated to be 224. If we take half of that at 112, we see we get a median pore diameter for the area distribution of 0.00903 micrometers or 9.03 nanometers. These medians mean that in the case of volume, 1/2 the volume was found to be in pores larger than this diameter, and 1/2 the volume was found to be in pores smaller than this diameter. And from the area distribution, 1/2 the total pore area was calculated to be in pores larger than this diameter, and 1/2 of the total pore area was calculated to be in pores smaller than that diameter. Now you might say, well, what's a good average diameter to use for this distribution? And one way of doing that is to go back to the relationship between area and volume of a cylinder. If we had a single cylinder that had this volume and at the same time had this area, we could calculate its diameter by saying diameter is equal to 4 times the volume divided by the area, and in the case of this sample would be 0.00930 micrometers or 9.3 nanometers. So it is the average size that can explain this area and this volume at the same time. Now we mentioned bulk density earlier, and basically by using a calibrated penetrometer, by using the assembly mass during the analysis, as well as the penetrometer mass and the sample mass, along with the density of the mercury, we can calculate the volume of mercury displaced by the sample essentially at the lowest pressure taken. Or as you saw with the porous powder, we can adjust the pressure at which we calculate the density if we want to remove the effects of interstitial filling. But that gives us a bulk density from a bulk volume determined essentially gravimetrically and from that calibrated pin volume. And that's why it's important to calibrate the penetrometers. Now, we can also calculate a density that corresponds to that after we have filled the pores. We call that the apparent skeletal density, taken at the highest pressure. And it's basically the bulk volume here corrected for the intrusion volume to give us an apparent skeletal volume. Dividing that into the sample mass gives us an apparent skeletal density. This would be similar to that you might obtain by gas picnometry. You do have to make sure that mercury filled all available pores that the gas can move into, and also that you've corrected for any compressibility. But generally speaking, for a material like this, it should come out pretty close. Now I can calculate a percent porosity. In this case, I can use this intrusion volume as the pore volume, the reciprocal of this bulk density as the bulk volume, and porosity is defined as pore volume divided by total or bulk volume, and in this case is almost 62%. It does show the range over which we're reporting. This is the full analysis range, so we didn't do any editing on this sample, and it shows the equivalent pore diameters that match those. So that's a typical intrusion summary. And again, I've been asked many times what those mean, and I wanted to use that as our last and 10th tip. But again, by no means our least important one. Thank you for your attention today. I hope that this demo will help you to better use the AutoPore to determine reliable material porosity and density results. Please feel free to contact us if you have any questions or comments on the AutoPore operation and the results it produces. And feel free to visit our website where you can find more information on the AutoPore and all of our products. Be sure to stay tuned for future presentations on our instruments. Thank you again.